In this video, I want to give you a quick tutorial about how to construct flood frequency curves. I'm going to use the same idea I had last time, which was to show you how to do this in Excel, even though for a relatively small data set like this one, you don't need to do it in Excel, but Excel makes things a lot easier just to show you, and I can graph things more easily, etc. So here we have, I think, let's see, I think that's 17 years of peak stream flow data for the Suwannee River, again in Florida, near Benton, Florida. And you can see that in 1978, the largest discharge observed was 6,030 cubic feet per second, etc. So these represent the peak annual discharges. And our job is going to be to produce a flood frequency diagram or graph from which I can extrapolate and infer the probability, exceedance probability for floods that are actually much rarer than ones that would typically occur in 17 years worth of data. For example, floods with a return period of, say, 50 years. So how do we go about doing that? And actually the techniques are very similar to what we used for flow duration curves. So the first thing we're going to do is we're going to determine the rank of these discharges from 1, the largest, to 17, the smallest. So we'll call the rank M, right? And once again, I can look down and I can see that, let's see, the largest is here. And then the next largest looks like it's here, and then 3, etc. And once again, I can take advantage of the fact that Excel allows me to sort these data really easily without any trouble. So I'm going to sort all these from largest to smallest on the discharge, and there we go. And so now I can quickly fill in the ranks from the largest discharge, peak annual discharge, to the smallest. And there were 17 years of data. And I now want to plot these up to create a flood frequency curve. Now remember, for the flood frequency curve, we're not going to be using the exceedance probability. We're going to be using the return period, also called recurrence interval, also called exceedance interval. And so what we're going to do here is we're going to, let's see if I can make sure I get this right. There we go. So we're going to use the idea that the return period, remember, the return period is equal to the reciprocal of the probability. And remembering that the probability we estimated as the rank divided by n plus 1, where n was the number of years of data. Therefore, we can say that the return period, whoops, I'll do it up here, can be expressed as n plus 1 over m. It's just the reciprocal of that expression. So that is how I'm going to calculate the return period in years for each of the discharges, peak annual discharges shown in column B. So what I'm going to do for each of these is take n plus 1. Well, there were 17 years of data, so that's 18 divided by the rank. So for the very first, the largest peak annual discharge I saw, the return period is estimated to be 18 years, and we can calculate the return periods for all the other discharges as well. Maybe I'll give these another significant figure so you can see that they're actually slightly different when we get down near the bottom there. There we go. So those are my return periods estimated for all of the discharges shown in column B. And once again, I'm going to plot the return period now against the discharge. And again, having to do this silly Excel thing here, I'm just going to take this data and copy it over to here so that when I grab these two cells, it will assume that the one on the left is the x-axis. And I'm going to insert a graph here. Let's see, a chart. We're going to make it a scatter plot. That's what it looks like. And that's what my data look like now. So now I want to connect these. Now hold on a second. Actually, at this point, remember, these are our data, and we have estimated return periods from about 1.1 year down here all the way to 18 years over here. But remember, the idea here is we want to draw some kind of line through these data. So let me sort of show you in theory what we want to do here. I want to draw some kind of line through these data like this. going to fit some kind of curve through the data. And then really importantly, I want to extrapolate this to higher values of the return period for higher discharges. I would like to know, for example, what is the return, how large would a discharge be that has a return period of 50 years? Well, we don't have 50 years worth of data. That's going to be a discharge larger than anything we saw in 18 or 17 years. And so we're going to need to extrapolate this curve. And so the shape of this curve is really important. And so what we often do is we will transform the x-axis into something that will make this curve easier to extrapolate. Now, there are several different ways to do this. Some of them are more rigorous than others, but I'm going to describe a real simple way which works a lot of the time, and that is simply to use a logarithmic scale for the exceedance interval along the x-axis, the return period or exceedance interval or recurrence interval along the x-axis. So I'm going to change this to a logarithmic scale, and actually I'm going to do this real quickly here because I have a clever way to do this here. Let's see, I'm going to change this to, there we go. So I have done all this at once because I can do this in Excel. And notice what I've actually done. I simply changed the x-axis to be logarithmic. And notice that when I do that now, my data points fall kind of pretty close to being along a line. And this is very often the case. It becomes more of a problem sometimes when I have a lot of really small data, and a lot of times the data won't look very linear at small values of the, let's just make sure we understand actually what we're plotting here. I should probably have done that. So let's see. Let's just make sure we know that this is discharge over here, and this is the return period I'm plotting here in years. So often these data will look a little non-linear on this kind of plot down here at low values of the return period. But in here it actually doesn't look all that bad, and we can certainly good enough to use a straight line fit to these data. And the beauty of this now is that now this allows me to use this part of the relationship, which is beyond the data we have. Remember, that's 18 years right here, to actually make inferences about the relationship between the discharge, peak annual discharge, and the return period. So, for example, let me clear that junk up there. Having this relationship, I could say, well, what is the 50-year peak annual discharge? What is the discharge that occurs on average once every 50 years? And I could find that as follows. I could say, okay, we go to 50 years. There's 10, 20, 30, 40, 50 years is this line here, right? And at 50 years, right there, the intersection of the 50-year return period with the curve gives me a peak annual discharge of 24,000 cubic feet per second. 24,000 cubic feet per second is larger, much larger than anything observed in my 17 years. But by extrapolating the observed data, I'm able to infer that the 50-year return period peak annual discharge would be about 24,000 cubic feet per second. And that's the real utility of this method. It allows us to extrapolate beyond our observational data to extrapolate to values of the return period and discharge that are typically larger, but sometimes smaller, if that's what we're interested in, than what our data actually cover. And in this regard, it's really important that we get this fit right. I mean, if we don't have much confidence that our data are fit by this particular relationship, then we don't have any confidence in the extrapolation. But in this particular case, straight line log linear fit looks actually pretty darn good, and so we can be pretty confident that, well, fairly confident that this line is a good fit to our data and that this inference of a 50-year return period peak annual discharge is pretty robust. And that's the technique we're going to use in this class. Instead of trying to deal with different kinds of models, statistical models for the distribution of the return periods, we're going to assume that they can be best fit with they can be simply fit well enough with a logarithmic, semi-log graph where we're plotting the log of the return period versus a discharge. We're going to try to fit our best straight line through the data and use that straight line to make inferences about the relationship between return period and discharge. Notice there's a couple other ways we can use this relationship. For example, we might ask the question, let's do this let's see, in red here. We might ask the question, well, how often would we see a peak annual discharge that equals or exceeds 21,000 cubic feet per second? Okay, there we are, 21,000 cubic feet per second. Maybe that corresponds, using a rating curve, to a stage that creates flooding. So we want to know, well, how often does a peak annual discharge of 21,000 feet per second, cubic feet per second, occur? We can use the relationship we have here again. We can go over, and following that over to there, it looks like it occurs about once on average every 28 years or something like that, somewhere in here, right? If I go follow that curve over. So we would say, okay, a peak annual discharge of 21,000 cubic feet per second happens on average once every, what did I say, 28 years, if this is 28 years. And notice that if this is the return period for a peak annual discharge of 21,000 cubic feet per second, we could equivalently say that, hey, a peak annual discharge of 21,000 cubic feet per second is equaled or exceeded 1/28th. That's the probability that it will be equaled or exceeded. That number, I can't do that in the top. Well, we can figure it out. Let's see what that is equal to. Equals 1/28th. That's equal to, express that as a percentage, 4%. So 4% of the time we would expect a year to happen where the peak annual discharge of 21,000 cubic feet per second or more occurs. Only 4% of the time. And that's super useful information. For example, if we were trying to plan for flooding or calculate insurance rates on a house, or any number of reasons where we might really want to know the likelihood of a discharge of a certain specific size being equaled or exceeded.